Now, this brings us back to something that we've actually already seen. We already talked about a little bit. These are our general keto structures. Now, the same sort of operation works with our ketoses as it did with our aldoses in terms of kind of building the molecule up. But what we're going to do is we're basically going to be inserting something between carbon 2 and carbon 3. When I say something, we're going to be inserting this between carbons 2 and number 3. Okay, so our penultimate carbon is still going to dictate whether or not we have a D or an L sugar. And we see D-erythulose. Well, we can make L-erythulose, in which case that hydroxide group would be on the left-hand side of it, or on the left-hand side of the structure. Okay. Now we can take that a step further when we look at our 5-carbon variations of our ketoses. There are only 2 of them. If you remember, how many 5-carbon structures were there of our aldoses? Well, there were 4. Why is that? Well, let's see what makes D-ribulose and D-xylulose similar and different from one another. What's similar is carbons number 2 and carbon number 1, identical. Carbon number 5 would be identical. Carbon number 4 is going to dictate whether or not we have a D sugar. And so that's arguably something we don't have to worry about. And so I'm going to go ahead and scribble all these out. The only ones that we kind of care about, well, it's carbon number 2. Carbon number 2 is going to dictate our specific name, our common name for a sugar that's used. So we've got D-ribulose and D-xylulose. Or carbon number 3, I'm sorry. 3, not 2. D-ribulose and D-xylulose, well, it's going to be an OH group on the right-hand side or an OH group on the left-hand side. And that's the only variation between those 2 sugars. Okay, so that's all that varies there. Remember, when we were talking about our D-aldoses, we had 4 5-carbon structures. When we talk about our ketoses, we only have 2. Because, well, that ketone functional group is going to dictate kind of the almost structural flexibility, the options that are available. Okay, next up, our 6-carbon molecules. Carbon number 1 and 2, we're going to scribble those out. We don't care about those. In all of these structures, carbon number 6, we don't care about. Carbon number 5, that's our penultimate carbon. And as our penultimate carbon, that's going to tell us our D versus L structure. And that leaves us with, well, only 4 possible structures. Now, D-cyclose, well, D-cyclose and D-fructose, how are those 2 sugars related to one another? They are C3 epimers, because carbon number 3 has the only variation there. Okay, now if you remember, we talked about fructose as basically the ketose form of glucose. And that all stems from carbon number 3. If you remember, our glucose model was RLR. So C2, C3, C4. Well, in this case, we've got the L and the R for C3 and C4. We couldn't do anything with carbon number 2 because that's our ketone, or our carbonyl oxygen. So this kind of shows all of our relationships, and it's similar, but a little bit, well, I don't know. I don't even know if I would say it's different. I would say that if you wanted to commit something to memory, like I said, I'm not going to be asking you to commit things to memory. Instead, I would want you to look at these structures and, given this information, which one is the relationship between which sugar and everything like that. But if you, I don't know, if you were betting somebody on committing something to memory, ketoses versus aldoses, or ketohexoses versus aldohexoses, I would take the ketohexoses because there's only 6 of them, compared to there's 8 aldohexoses. So there's basically your structure of those. Okay, now what makes all of these structures, all of these molecules particularly interesting is we were just looking at the linear form of them. We were looking at only the linear form of them. However, what's important to recognize is that these aldehyde and ketone carbons are electrophilic. Alcohol oxygen atoms are nucleophilic. Okay, so when you think about these alcohol, if we look at something like glucose, which I'm going to go ahead and draw glucose out, we've got a hydrogen, C, it's 4, 5, 6. We've got an OH and an H. Okay, RLR was my system. OH, H, OH, H, OH, H. Now, okay, so we've got, let's see, an alcohol oxygen is nucleophilic. How many alcohol oxygens do we have? Is this one? Yeah. We've got a grand total on glucose here. We've got a total of 5 alcohol oxygens. So these are all nucleophilic. Now, when aldehydes are attacked by alcohols, hemiacetals form. So we've got our aldehyde, which we've got an aldehyde right here, and our alcohol, which we've got an alcohol here, 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 here. All of these groups are capable of attacking this partial positive group, that carbon there, because we've got these lone pairs of electrons there. Now, what that means in the formation of this hemiacetal is basically our basis for the cyclization of a sugar. The same thing occurs with a ketone functional group in an alcohol. A ketose can cyclize. So what you're going to be forming there between a ketone and an alcohol is a hemiketal. So this is the foundation for how a linear sugar that we were talking about forms the cyclic form. Now, I'll have you know that cyclic sugars are much more common and much more biologically relevant due to this fact, or due to this kind of due to these structural features, due to these structures within these molecules. Now, this shows our cyclization of the monosaccharide D-glucose. We know that it's a D-glucose because on carbon number 5, we've got our hydroxide group on the right-hand side. Carbons 2, 3, and 4, we've got RLR. We've got our partial positive up here. We've got our partial negative, our nucleophilic group right here. And so what we're going to do is this alcohol right here is going to be attracted to that carbon. And we're going to have that nucleophilic alcohol attack the electrophilic carbonyl carbon. And that's going to allow for the formation of our hemiacetal. Now, that linear carbohydrate forms a ring structure. So that ring can go into one of 2 different permutations. So that, keep in mind, this is carbon number 1. It's highlighted, it's indicated right there. Now that carbon number 1, it is going to, whenever it forms that hemiacetal, is going to have an OH group, and that OH group can either be kind of positioned up or down of the molecule. This right here would be my example of down, and this right here would be up. So alpha D-glucopyranose has an OH group pointed downward versus beta D-glucopyranose has it pointed upward. Now, what that ultimately means, and we'll get to the alpha and beta designation, but basically what you're looking at is where's the hydroxide group on carbon number 1 and where is carbon number 6? If carbon number 6 and the hydroxide group on carbon number 1 are in opposite directions, so this carbon 6 would be up and this one would be down, well, that's the alpha form of the sugar. If carbon 6 is up and the OH on carbon 1 is also up. That's a beta form of this sugar.